So it looks like a proof by induction. If every segment of a well-ordered set is isomorphic to an ordinal, the whole well-ordered set is isomorphic to an ordinal. So to some ordinal, right? Then the whole thing is itself also is itself order isomorphic to an ordinal. So, proof. Right, by corollary 318, if any initial segment of the well-ordered set is order isomorphic to an ordinal, it's order isomorphic to at most one ordinal. So we can define a function which goes from initial segments of A to the ordinals isomorphic to those initial segments. So we can define a function f which assigns to initial segments AB of A for any B in A here, a unique ordinal f of B so that if I look at AB, this is isomorphic to this ordinal f of B. So it's just dependent upon B here. So the picture would be, here's A, here's a typical B, and here's an ordinal f of B. So this is an ordinal. And this is isomorphic to the initial segment of A below B. So the previous, to say it over again, the previous corollary says, if I've got a well-ordering isomorphic to an ordinal, it's unique. The hypothesis of the lemma says every one of these ABs is isomorphic to an ordinal. Okay, so we'll just let f of B be that ordinal that AB is isomorphic to. And basically, the proof just runs, we're going to put all of these f of B's together and construct an ordinal which A is isomorphic to. Which is the natural thing to do. I know all the initial parts of A are isomorphic to ordinals. I'm just going to stack the ordinals up. So we're going to take, in the notes, I said let Z be the range of F. So that just means the collection of these FBs. So to spell it out, Z is the collection of FBs such that, okay, there's a B in A, and there is an isomorphism, GB, which goes from AB isomorphically to FB epsilon. This is GB going across there. Sorry, it's invading the picture over on that side. Now I've written GB here because what we have is that the order, the previous corollary said, if this is isomorphic to an ordinal, it's unique. Let's call it FB. But there's another lemma that says if I've got an isomorphism between an ordering, well, and another ordering, it's well orderings, then it's unique. So I'll call this unique isomorphism between here and here GB. So GB is appealing to 3,6. The isomorphism between AB and FB is unique. So we call it GB. And now we just want to argue that we can put together the FBs. So there's some things to observe. If I've got C and B in A, and C comes before B, so C is down here, then everything that comes before C is exactly the same as the things in the initial segment of AB that come before C. After all, AB is just an initial segment of A, and we're only worried about the stuff that's below C. Okay, so the point to be made here is that if C is below B, f of C cannot be f of B. It would be f of C. Because if f of C was equal to f of B, if f of C equal to f of B, then I could use GB to take AB and follow that by GC to the -1, the inverse of GC. This would take AB to, and these are both isomorphisms, isomorphically to AC. But this is an initial segment of AB. And this can't happen. There isn't an isomorphism between a well ordering and an initial segment of itself. So again, this would be a contradiction. Okay, so we can argue that FB and FC must be different. So what have I established? I've established that F here is 1-to-1, and also it's order preserving. By the same reasoning, sorry, I don't know, I want to, no, I won't say that bit yet. That comes later. So if C is different from B, f of C is different from f of B. So what we have shown is f is 1-to-1. Okay, are there any questions? Yes, you weren't blessing me, unfortunately. Okay. Okay, so f is 1 to 1. And since z is defined to be the range of f, it's a bijection between z and the collection of initial segments. And so is there's a bijection between A and Z. So ultimately, I'd like Z to be an ordinal, and F to be my order isomorphism. Well, I've got that it's a bijection, so I just try and verify the rest of that. So there's a comment that says that we should have, right, that F is an order isomorphism, i.e. F takes a, with its less than, isomorphic to Z with epsilon, right? If it was order preserving. And one will, and what I've labeled as 1 below will show that. Which it will be at clause 1 below. Okay, so let's justify that. So still with C coming before B, again, but going back to my diagram, I have GB going across the top here. Let's rename this as GC is going over here. So I think of GB and I just restrict it to AC here. Let's do another diagram. Let's clean it up. Here's A, here's C, here's B, and here is f of B here.
Can you move the paper down, please?
Oh, I'm sorry. All right, so I'm trying to make a cleaner diagram, another diagram here. So here's GB going across here. Here's GC going over here. So here is AB. This smaller bit here, this is AC, which is the same as AB, cut down to C here. And this is going over to F of C. Okay. Okay, so we're still taking C below B, as in this picture here. Right? Then I think of GB cut down to AC. So I think of restricting this top map here to this. And this is where exercise 3.4 comes in. This is isomorphic to f of B This is exercise 3.4. All right, let me put back up 3.4. That said, if you've got some f between just these well orderings here, which is an isomorphism between these well orderings, right? Then if I just restrict f to an initial segment, it'll send this initial segment over to, well, the initial segment over here below the f of z, which is what I've written here. So this is an instance of this. Right? So this is my z over here, or my x sub z, right, in the exercise. This is being taken over to here, this thing. Right, which is GB of C. So this is by an application of 3.4. Now again, repeatedly using the same building blocks over and over again. An isomorphism, right, between two well orderings here is unique. Well, we've already got an isomorphism between AC and FC. So it's going to have to be this. So again, by a uniqueness of isomorphisms, GC must be this. Must be this GB restricted to AC. And f of C is just f of B cut down to GBC. Restating what's there in the exercise. So this here has to be GC. So I've got here this initial segment of an ordinal, FB cut down to this, and this initial segment of an ordinal here, this must be, right, a member of f of B. This is by 312. Right, so every element of an ordinal is isomorphic to the initial segment. Sorry, every element of an ordinal is itself an initial segment of that ordinal here. So what I've got here is this initial segment of f of B. This initial segment, in fact, f of C, it's a member of f of B. f of c here is a member of f of b. It's an initial segment, therefore it's a member. So I'll write this all out as one, somewhat redundantly. What I've got then is that f of c here, this is f of b cut down to gbc, yeah, and this is a member of f of b. So putting this together with this up here, and this is a member of. So to sum up, I've got that this big capital F, right, it's a bijection onto Z. Right? And we've got that the map is order preserving between the less than of A and the epsilon of Z. So all that's missing is, I'd like to say that this F takes A onto the ordinal Z. So all that's missing is the fact that Z is an ordinal. To summarize at the moment, right, what is F doing? Sorry, to Z, not the integers, Z epsilon. And I know that it's an isomorphism. I just want that Z is an ordinal, and then I'm finished. Okay, what is an ordinal? A transitive set well ordered by epsilon. So, because F is an isomorphism, and this is a well ordering, this is a well ordering. So epsilon well orders Z, since less than well orders A, and F is an isomorphism. So we need that Z is transitive, but that's also easy. Why is Z transitive? Okay, what is a typical thing in Z is some f of b. I pick a u that's in f of b, and I want u to be in Z. GB takes the segment of A below B onto this. So something gets sent to U. So as GB is onto F of B, U is GBC for some C or other, which comes before B. Right, so the sum C in the initial segment in AB, in the domain of GB, which sends C onto this U here. But then we just write out and see what this is. Remember that f of b is an ordinal, and the elements of the ordinal are the same thing as the initial segments. So any initial segment of the ordinal is itself, right? Any initial segment of the ordinal determined by an element is that element itself. So again, this is, I never memorize which lemmas are which. I think this is 3.12 again, right? It's 3.12. And we have that this is, well, that's just what U is, GB of C. Right? And by one above, this is F of C. Right? So this is F of C here. F of B cut down to GBC is F of C. So this holds by one above. And this is because F of B is an ordinal. And lemma 3.12. This equals here. So the upshot is that U is in the range of F. So U is in Z. And this means Z is transitive. Typical element of Z, typical element of that. Right? Hence, Z is transitive and is an ordinal. So we're done. So we saw then that A could be seen as being isomorphic to an ordinal. So it's kind of like an induction, right? If all initial segments of a well ordering are isomorphic to an ordinal, the whole thing is isomorphic to an ordinal. Any questions there? Okay, we're going to write some of this out as a classification theorem for well orderings. So it's a little tricky, that lemma proof. You'll need to go over it again, I'm sure. Right? So it's quite a lot. It's quite intricate, the argument for what it's proving. So representation theorem. So this is 320. Representation theorem for well orderings. So every well ordering is isomorphic to an ordinal. And a unique ordinal. Right, so the last lemma justified that there was exactly one ordering. The previous corollary said it could be at most one ordering. And actually that's what's stated here. Uniqueness. This was corollary 318. So existence will follow from the last lemma. So I should have said every well ordering X less than, I was sticking to the notes, every well ordering X less than is isomorphic to one and only one ordering. So I'll get that X with less than is isomorphic to an ordinal if all its initial segments are. So this will be isomorphic to an ordinal if all its initial segments are. Okay, so suppose now I take Z to be the collection of objects in X, the V's in X, such the initial segment determined by V is not isomorphic to an ordinal. I'd like Z to be empty. I'd like all the initial segments of X to be isomorphic to an ordinal, because then I can deploy the last lemma and conclude that X is isomorphic to an ordinal. So if Z is empty, by the last lemma, we're done. So otherwise, let V0 be the least element of the least element in X under less than, which is in Z.
Move the page up, and there's also a question in the chat.
Okay, thanks. Least element of Z. What's the actual definition of the half triangle thing? What's the half triangle thing? Sorry, Jess, can you say what you mean by that, or can somebody tell me what the half triangle thing is? You mean the curly less than? This thing? This one? Yeah, this is restriction. So maybe I've got a function from A to B, and I have that C is a subset of A. Then F restricted to C is just the piece of F that sends C to something. Okay, so it's a restriction of F. So it's the same function as F, but it's just the piece of F whose domain is C rather than all of A. Okay. And Ryan asks, something is isomorphic to one and only one ordinal, surely, rather than ordering. Yes, thank you. Yeah, it's correctly written in the notes. I miswrote there. Thanks, Ryan. Okay, so where were we? We're looking at the collection of elements of X, such the initial segment determined by the element is not isomorphic to an ordinal. And if this is non-empty, we let V0 be the least element which is not isomorphic to an ordinal. So anything shorter is isomorphic to an ordinal. So if I look at xv0 with less than here, this is a well order. It's just an initial segment of the well order X.
Can you move the page up, please?
Sorry, but all its initial segments are, because V0 is the least one who's determining an initial segment not isomorphic to an ordinal, all the initial segments of this are isomorphic to ordinals. But all of whose initial segments, so things that look like this, okay, for some W that comes before V0, right? So, I mean, here will be X, here's this V0, initial segments down here determined by W's below V0. These guys are all isomorphic to ordinals. And XV0, this is just the stuff below W here, right? These are isomorphic to ordinals. Because W is less than V0. So such W are not in Z here. But now the last lemma then just says all the initial segments of this isomorphic to well orders. This then would be is not a well order. So this is not a well order, but all its initial segments are. This contradicts the previous lemma. Previous lemma, this would mean that XV0 is isomorphic to an ordinal. So that's a contradiction. So Z is empty. That's all we're left with. And we're done in that case. So we can use that lemma then to give that representation theorem. Okay, fine. Next time we'll continue in the text, of course. We'll look at properties of well orders, and we'll get on to the Burali-Forti paradox next time, and then look at some concrete examples of ordinals defined from various kinds of orderings.